Yeah, the iPad is its audio. Okay. Well, let's get started. So, hello all, welcome back to week 2 of ACM Quantum Initiative. Reese Takahashi, and this is Tao. And we'll be through the math fundamentals of quantum computing. We're going to be doing a bit of a boot camp this week, but most of the stuff we're teaching this week should be based off what we expect to learn in high school. So we'll do trigonometry and the simple vector stuff. We want to make sure that everything that we teach is very intuitive, and we on it in further weeks algorithms. So I would like to explain that compute not a trivial in any matter, but at least the mathematical foundations can be simplified and separated into a more readable format. And I'd stress that we want to make sure that you guys are learning this completely. So don't feel free to ask any questions, and don't stress about if you don't know any of the concepts. We'll be reviewing them quite a lot. And so I would like to right here explain. Oh, it's laggy.
Oh, yeah. Okay.
This, like I said, this week's session provides a brief overview of mathematical associated with quantum computing. I would like, unfortunately, for my interest, most quantum computing is math. It's a little long, so if you're out there, but this play on it.
It's like 5 seconds.
Yeah. We'll be linking, we're going to be using IBM Quantum Composer, which is a visualization tool for the mathematics and further on to the quantum algorithms. It really helps like visualizing what's happening. I will post the link in the Discord real quick, actually, just so if you guys are using desktop or laptop, it's much easier to get to. Resources. There. Yeah, you don't need an account to use it. So, and I'll get to like the interface and how it works later on once we start the workshop. So I would say this is for being a sandbox tool. It is very powerful. It's actually mostly limited by the fact that you don't have good software tools to make even bigger algorithms or more complex algorithms. But fundamentally, it describes everything you can do with a quantum computer. And then here's just a short list of what we'll be talking about today. I'll be talking about complex numbers, and then the Tao will be talking about matrices and vectors and broadcat notation. And I'll return to talk about quantum bits and qubits, and I'll bridge us to our lecture in quantum data, quantum operations. So I will actually show hands. How many of you here pretty much known all the complex matrices through and through in their education? Everybody?
Like AP Math.
Okay. So hopefully this is not just review for you all, and that will actually teach stuff. So I'm going to start off with complex numbers. If anybody remembers the quadratic equation, polynomials can have imaginary roots that don't cross the real line. Number I to represent the square root of -1. And there are 2 major forms for how complex are represented. Your rectangular form, which you might see in math, and then your polar form, which you might see in electrical engineering, and will be more often used in quantum computing. The big jump in the polar form is that there is there's an amplitude R and a phi. And it'll be based off the Euler's identity, and we'll show you that in a little bit. But the reasoning behind we use polar form is because how we do operations, amplitude is generally treated separately from phase in certain operations.
So just a side note, what is phase? Right now you can just think that it's some kind of angles, just a fancy name of angle. And another side note is that some like electrical engineering background researchers will use J instead of I, because I is sometimes used to represent current. But if you see I and J here or here, it means the same thing, just the imaginary part.
Mm-hmm. And theta is if you trig just angle on a unit circle. And actually, we'll go a little bit more into that. So you got your Euler's formula over there. If you remember, e to I pi equals -1. Well, that generalizes to any angle from cosine theta to I sine theta. And e to I theta is considered, like a direction. So it always lies on the unit circle, and your R is your magnitude. Yeah, complex exponentials and geometry are very tightly related, and you'll see it in solving differential equations all the time. And I cannot enforce that how much that complex numbers are really what drives the ability of quantum computers. So there's some simple operations very similar to what like a real number has. When with addition and subtraction are exact same. You just think of I as X, you get there. But with multiplication and division, you get into some weird circumstances where you have to remember that I squared equals -1, and that will rationalize that number. And so the division is very much the same, and this does it a little bit of justice for what's operations happening. So you can actually see that the C minus I is something called the complex conjugate of this. If you're math, you want to rationalize your denominator, and so you can multiply it by something that is equal to 1, and you can see the entire in the denominator. This right here will be pretty much your angle representation. And actually, we'll go right into the conjugate and modulus. So complex conjugate is pretty much just derived from your division right here. These two, C plus di and C minus di, are conjugates of each other. And what they do is if you multiply a complex number by a conjugate, it rationalizes the whole thing, right? It'll be an entirely real number. And that is actually what is interesting about the property of a modulus. A modulus shows describes its distance from the origin squared pretty much. And so if you get 3 minus 4i, its distance is 5, whereas amplitude is 5. And let me see. And it actually, this is again, you'll see the modulus part quite a bit, but the rectangular form where it's like minus I and plus I, that's already abstracted out in Eulerian form with the theta.
Yeah, so I will carry on with the vectors, and I will probably just write some random notes on the slides. Hopefully you guys can see it. Oh yeah, okay, let's go on. Yeah, vectors, the definition is very rough. It's like an older collection of elements, but in our field, you can just think it as an older collection of complex numbers. So you will have row vector or column vector, but by far you can not really tell the difference between these two. But we will go on how different they are when we are doing matrix multiplications later on. So just like the modulus part, we can also calculate the distance or the length of the vectors. So it's basically the sum of the square of individual elements inside the vector. Is very simple. And just some mathematical examples here. Again, we have a vector with 3 and 4 in 2 different dimensions. So the length is very easy to calculate, is 5. And again, in 3 dimensions, we have 3 items to square off. and the result is 3 as you see. And the second important operations is the dot product. So it can be considered as some kind of projection of one vector in the direction of another vector. So to visualize it, you can just like have a graphical representation here. So what is projection? So if I call it vector A and vector B, the projection of vector A in the direction of vector B is just like just imagine there's a very big sun over here, and there's some shadows if you consider vector A is a road. So this is like, I would like to create a projection. And you can also like infer from the geometric representation in formula 12. It's just the length of individual vectors, product of each other times the cosine theta. And the theta is just the angle between these two vectors. And you can see that the length is just the length of the original vector A times cosine theta from your basic trigonometry. And I provide some visual example here. Yeah, there's some properties you guys may want to know. So if two vectors are 90 degrees from each other, we would like to describe these two vectors are orthogonal. In this case, because cosine 90 is 0, the dot product result is always 0, no matter how you vary the length of each vector. And if two vectors are of the same direction, which means that the theta is actually 0, the dot product is just the product of their lengths, as you see. And if they are 180 degrees apart, well, it's another version of the product of their lengths, but you have to time -1 because cosine 180 is -1, as you know. So you are free to explore this example later, or help you to calculate some like a vector multiplication in your homework. I don't know. Okay, let's continue. Okay, yeah, this graph I already hand drawn it before, so let's just skip it. So matrices is like two-dimensional arrays, and to describe its shape, we can describe it with k rows, l columns. So the formula shape is k by l. So in this case, we have two rows here, 3 columns here, so it's 2 by 3. It's very easy to remember. To extract the specific element you want within a single matrix, we have like a coordinate system inside the matrix. So if you want to have the KL's element of a matrix, you first locate the K's row and find its intersection with the L's column. We can visualize it in this example. So A31, we first locate row 3, and then column 1. The intersection is this one, number 8. So yeah, it's like a very simple question. So what is A22 in this matrix? 5, right? Okay, just check our sanity here. And let's go on matrix multiplication. If you have studied matrix, this will definitely come directly after the concept part of matrix. But I think the idea here is just to get you guys familiar with this kind of very abstract representation of mathematical operations, because you will see this kind of abstract form very frequently when you go on to the algorithm part, because you have to deal with solve different input lengths. So you don't have to work on a very specific shape. And this kind of abstraction provides generalization as well. So to interpret this formula, we can directly go through this example here. So C is the result of matrix A times matrix B, and C is here. The right-hand side matrix here is these two. So In this case, A shape is 2 by 3, B is 3 by 2, so C is 2 by 2. Okay, remember the matrix entry. So if we want to calculate the C2, 1 here, in this case, we have defined I is equal to 2, J equal to 1, and we can just plug in this very abstract formula. So I here can vary. Oh, no, I here is fixed, but the K can vary. And also J is fixed here, but K can vary. So if you vary K, but we fix I, it basically goes through A21, A22, A23, which is exactly the row here. Similarly, J equal to 1, but we vary K. It's basically iterating through this column. So you can just interpret like a matrix multiplication as something like a kind of organization of dot product of row vectors and column vectors. And you can probably see here that to complete the dot product, we have to ensure that the number of columns of matrix A have to match the number of rows in matrix B. And this property is summarized in the next slide. We see here, these two dimensions need to match, and the result shape is M by P. The second property is very, very important. If we shift the order of matrix multiplication, the result is not always the same. This is important when you try to design circuits later on, because later on you will know that apply a quantum gate in a circuit, basically if we apply quantum gate first and then apply quantum gate B, the result is not always the same as apply quantum gate B first and quantum gate A. You really need to remember these important properties here. Are very easy, but this one is like a design principle you need to remember. The last two properties is more like the matrix version of scalar multiplication. You can use parentheses to define what part you want to calculate first, but you just need to make sure that the order of calculation is the same. And finally, you can also distribute the multiplication into like a summation of two parts you want to calculate first. Also, in our field, sometimes we want to interpret the matrix multiplication, like geometrically way. So we can use two-dimensional multiplication as an example. So we have a matrix I would like to call R here, and we do it after before 2D vector. The result is also 2D. So before and after the matrix multiplication, we can always visualize the input and output of our result in some kind of 2D places. And there's some like special R here. The first one is like a rotation, which means that we have a unit circle here. If we input a unit length vector after the rotation, the result is always on this unit circle. And probably you can think that any kind of matrix multiplication in 2D can be visualized in the combination of first we will apply a rotation, and then, for example, if our output is a longer matrix with scaling here. It's just a side property, but I don't think you guys will need to use it very frequently later on. But it's just very interesting to let you guys know. Tensor product, I think it's the last important operation you need to know to actually calculate something of your circuits. But the calculation step is pretty simple. You can directly jump to example 2 here, because the tensor product is basically ask you to do the product between each element of your left matrix with the entire right-hand side matrix here. So A times the entire right-hand side matrix, B times the entire right-hand side matrix, and so on. And if we have a matrix M by N, and another matrix A by B here, the result matrix, you guys probably can conclude from this operation, like the steps, the result matrix is AM times MB. So it's like a way to expand your matrices. To relate this kind of concept in the the length or some kind of operations to describe it very professional in our field, we will introduce the bracket notation. But the cat is actually just a fancy name of a column vector, and the bra is like a very fancy name of the row vector. I don't know why they have to define it, but probably we are born so late. If we were born earlier, we can just use column vectors and row vectors and no need to define these new names. Just another visualization to show that the cat is actually a column vector here. And if the dimension is 3, you can also visualize it in 3D place, just like global column vector here. As we, because we already talked about the complex, really empower the computation inside the quantum algorithms. So we need to remember that the elements of those column vectors and row vectors, they are not purely real. Sometimes you can get complex numbers inside of them. And they are really required to represent quantum states. Because if you think there's a vector with, potentially you can define the 1 plus 2j, 1 minus 2j here. The length of the both vectors are already the same, but it's really this imaginary part that really tells the phase difference. So just remember that you have to deal with complex numbers, and you need to be careful with that when you are doing calculations later on. So the first usage of complex number here is to transform into a bra. As we see, roll the way back here. If we have a bra times a cat, it's a row vector times a column vector. So if the row vector is 1 by n, the column vector is 1 by 1. The result is 1 by 1. It's a scalar. It's just a complex number. And if we want to translate a cat into a bra, you first just like some kind of light down and then take the conjugate. But why conjugate? Because if you remember from our modulus part at the beginning, 1 minus 3i times 1 plus 3i is 4 minus 9i squared. I squared is minus 1. So it's basically what 4 plus 9 is 13, which means it's real. So when you first take the light down version of the cat and then do the complex conjugate, and then finally you do the dot product, the result is always real. Yeah, it's another very abstract form of doing bracket dot product described here. So this symbol, like this asteroid here, is like doing complex conjugate. So other than that, it's exactly the same as the dot product formula here. And the example shown here is very simple, but I think this kind of real number dot product is always frequently used in our primitive programming algorithm course. Is there any question?
Why is one a row vector, one column vector dot one anyway?
Oh, you mean like the definition of? Oh, you first.
Yeah, if you go back to like matrix multiplication, your dimensions must match. And so it's kind of treating a vector like a matrix.
Oh, okay.
Yeah, because we say like the matrix is two-dimensional vector. So I think it's just some people would like to call it differently, but you can always call a column vector or row vector as some kind of special form of a matrix, 1 by n or n by 1. Yeah, notice that if you want to work on like in machine learning field, they will always use the column vectors, assuming that as an input, and you also have to deal with this kind of like a matrix multiplication. So at least this course is helpful, even if you decide to quit these quantum computing fields, or will be useful elsewhere. Okay, let's go on. Oh, vector basis. So I think when we start the like 2D representation, like the vectors in 2D, we are always having some kind of x-axis and y-axis here. And later on, we have 3D spaces. And then we have x, y, and z here. So what exactly are these like different axes? So axis is very related to this concept of vector basis. So if we take the unit vector in x-axis and unit vector in y-axis, basically we have 1, 0 and a 0, 1. Then every point in this 2D space can be represented as a linear compilation of these two basis vectors. And that's also true in 3D spaces. But in this case, we have 3 unit vectors, 1, 0, 0, 0, 1, 0, and the 0, 0, 1, which is just like the formula shown here. It's like a representation, or you can call it projection, some kind of the vector in 3D into 3 bases, which means that you project the vector into x, y, and z axes. And qubits, later on, you will find that they actually define a basis to doing operations in their representation spaces. And Reese will introduce that later, so don't worry about it right now. Orthonormal basis is like a most used form of like to say of vector basis. So remember, when you do the dot product between like these two, or these two, it's always 0. So from our visual example here, which means that the cosine theta is 0, which means they are 90 degrees from each other. So that's the ortho part, and it's the ortho part. So what is normal? Normal means that the length is 1. So again, back to our 3D example, there are only 1, and then other entries are just 0. So they're always like a unit 1 length. But as we said before, it's like only the angle between vectors are important in our field. So to like visualize it in a very, very primitive mathematical way. For example, we have normal x and y axis here, but you just like can rotate your screen. Or in this case, you can just rotate like this shape 45 degrees. You can always get another set of orthonormal bases. I guess you can always calculate how to transform the like a projection on x and y z base x y basis into our new basis. So originally on x y basis, we have a1 0 b0 1 of ab, and we just need to make sure that it's equal to the new basis, which is we have k over square root of 1 plus I'm going to call it n here. But it's just random notations. You can use whatever you want. And it turns out that kn is also unique when you are solving this equation, because you actually have 2 equations and 2 unknowns. So the answer is unique. Okay, let's go back to Reese to talk more about the qubits.
Okay. So I feel like everybody's probably heard about Schrodinger's cat before, but it describes something called a superposition state where something can have the probability of being both alive and dead at the same time, 50-50 chance. And so you see that it's interesting that it's not one half alive and one half dead. This is represented for the square root of their probability. So they call it probability amplitudes. And because it's a square root, you can have complex numbers, and it encodes some the phase information of those complex numbers, which is very important when it comes to certain concepts like interference, which if you remember ever sort of heard of light interfering when it comes to like double slit experiment or diffraction grading, it's specifically this complex phase that does it. And so, and it's what makes quantum, or I should say, there's more to quantum because it's quantized, but what makes quantum effects unique is the fact that they can interfere. And a big part of like these probability amplitudes is, and these are really probability vectors, is that they're required to be normalized. So a normalized vector, you know, its dot product will always be 1, or this the inner product, or even the broadcat of them all mean the same thing, means that it is 1. And so if you look at this expansion, that the orthogonal basis of alive and dead, dot to 0, and alive and alive probability square to 1, or the dead and dead probability will square to 2. This is actually not normalized. The total sum should be 1, but and like it says, normalized by 1 over square root 2 to get 1 over square root 2 squared is 1/2, and it's all sums to 1. And so, well, now I'm going to jump more into the deep end of like why we use all these vector notation and these complex numbers, because it's the non-trivial component of this. So I'm going to start off by just saying, why do complex numbers appear? I've said before, it's through interference, but it's easy to say that complex numbers arise naturally in quantum computation because they describe complementary and correlated variables. So the very first idea you can start with is if you have a coin and you do a coin flip, there are 2 distinct outcomes, right? You can either have heads or tails. And so we call those complementary or correlated variables. We have some parameter, usually theta is just a probability of heads happening. And in coin toss, that's going to be 0.5. So if you say that heads is a 0.5% or 50% chance of being heads, then you already know that tails is going to be 50% chance. And so these are considered complementary outcomes because their probability sum to 1. And the interesting thing about quantum mechanics is that instead of treating these probabilities dependent of theta, which is your parameter, quantum mechanics views this as measuring an underlying state of phi or psi. This state psi encodes both outcomes and is more fundamental than simple probability. And fundamental is a arbitrary term. It's a more convenient perception of it, because show of hands, do you think that that describing a coin flip as either heads or tails is representative of a coin itself? Maybe to a computer scientist, if you're simulating a coin flip, yes, but in reality, heads and tails doesn't completely describe a coin. It just describes the outcomes of that coin. And that is very important to how quantum mechanics interprets things. And then the thing that I described earlier was measuring. Instead of it being a single probability parameter, theta becomes psi, which is a unit vector in the space of measurable states. You know that there's always going to be, if you drop some probability of one outcome, you know that the other outcome is going to have to increase in probability. So preserve this unit vector. And just going back to Euclidean distance or even Pythagorean theorem with a triangle, you know that the square of a squared sum of any unit vector or the inner product will always sum up to 1. And so if we go back to our heads and tails example, you see that if the vector entry A and the vector entry B would correspond to the square root of the probability of heads and the square root of the probability of tails. And immediately you would think, oh, if the square root of the probability can be negative, then if you square it, you're going to get a negative probability, or a complex number. You can have a negative probability. Like just put in a equals I, and the square of a is going to be -1. Which doesn't make sense. And this squaring is actually just a more simple reduction of a more complex operation that we did talk about earlier. If you remember your norm squared or your modulus, that is the more complex number equivalent to a real number squaring. And so
we are really dealing with the distance for our region. We are doing squaring here.
Yeah, and that's where I said, like, where r times e to the I phi, they have different operations, is because we're treating r differently than we're treating e to the I phi. We have different uses for them. And so
before you continue, I would want to highlight that this is a very important topic, just because people take it for granted why you would want to square the amplitudes or think of probabilities as like squared numbers instead of just like a straight up probability. So if people have any questions, you can definitely ask them now, because otherwise it would stumble.
Yeah. And so what this hidden operation is, it's sometimes called a projective length or a norm onto an outcome. And if you remember, we call an outcome is just a basis vector in your orthonormal basis. So your probability heads will be that 1, 0 vector, your probabilities tails will be your 0, 1 vector. And
yeah, draw some those here.
Yeah.
Then to understand better.
Yeah. Let's see. So it's 1, 0, and b equals 0, 1. And when you measure the magnitude, it's always going to be a real number, right? You can't have a negative length to something. It doesn't make sense. So if you measure the magnitude, you have, for a real number with a vector, you have two numbers that have the same magnitude. It's the negative, like -1 and +1 will all square to 1. Where on the complex values, if you do this projective lengths, which is the complex conjugate or the modulus or norm squared, then you have an entire spectrum of numbers that have the same length, because a is just your magnitude, and your e to the I phi is just a completely different value that indicates your phase, your complex number, which will be discarded when measuring. You can't measure the phase of something in a direct measurement basis. So going further, complex numbers and inner products, you always have the complex conjugate or number multiplied by its complex conjugate to measure it. And I would just, before we go on, I would just make sure that people realize that psi is a unit vector, because if you go back, if you're under a unit vector, your normalization, your Euclidean distance will always be 1. And so I just want to do some like sanity.
Can you go back to the slides?
Mhm.
Can you explain what you mean by the space of measurable states?
Okay, so yeah, this is not I put it way too verbose than it has to be. It's just saying, all the measurable outcomes that can happen, right? You know that it's either going to be heads or tails. There's not like a third state it can be. So your space of measurable states is every measurable outcome you can get.
You can use your tail and head as example. So you should be a set of tail and head.
Yeah.
Oh.
So you'll actually, like, if I do the vector, so psi equals alpha of square root heads probability plus beta square root. This is bad notation, but it gives the point across. These heads and tails are all the measurables you can have. If you have another measurable state, it's just going to be added to your unit vector, because it's going to be a non-zero probability, and so you have, under traditional normalization, some squaring it, the length will be 1 of the unit vector.
And then why is it square root?
So if you think of like Pythagorean theorem, I would say, like right here, if you have a vector of length 1, or like 8, the hypotenuse of a triangle will always, c² equals a² plus b². it's just convenient. If C is always one, then you know that C squared is going to be one. So you know that A squared plus B squared is going to be one. It's a, if,
Oh, so if you square it, then you write it as alpha squared H plus beta squared T.
yeah, and if you want to think of it in a, like, for just two outcomes, there's your trigonometry will say, like, sine squared plus cosine squared equals one. Is because that on your unit circle, the length of your hypotenuse is always one. So I'm just gonna go back to the sanity check because this will hopefully explain this more to you. And is like, what does psi have to do with theta? They are essentially the same quantity. Theta has, you can use theta, and there's something called density matrix, which is another way of representing this data, but it uses a lot more, like its size is literally the matrix size of the matrix you're operating with. So it takes a lot more numbers, and it's unintuitive, its action, because you're working with probabilities here. So like a transfer from one probability just doesn't have a simple function going to another probability. And that's why we work in the psi basis, because we always know that the unit, any transformation, it will be a unit vector afterwards. And then complex values. So we said that A to the E to the I phi allows for an infinite number of complex amplitudes that equal, or complex vectors that equal amplitude length 1. And what's so important about this? And the complex phase is what causes interference in almost every circumstance. And so math says that complex numbers can exist. Science says we have measured the fact that complex values must exist. And so, I would say that how people describe this as a new computing frontier is they go from the basis of probability, like we did, and say that probability, there's always going to be a direct transfer of from one value to another, but because we can do a complex phasing, we can do probability transfers that is not represented in like classical probabilistic functions. And so I'm just going to start off by saying all of these, like A plus B, like your basis.
Elaborate on the negative
Yeah, so that's a, people love using that as a term to describe like the difference between like interference and classical probability, because it's interference kind of like, if you have the probability of something happening, interference can reduce that probability. So it's just like adding negative probability to an outcome. And it's I guess it's not like a often used term in actual quantum mechanics, but it is something people use to describe like interference as an action on state.
so it's like always the
Mm-hmm. And so going back to the starting off with binary was what we use for both classical and quantum computers. We have the what's called a quantum bit or a qubit, and that is, if you know, like heads and tails is just this is your heads outcome, this is your tails outcome, and it scales up from there. You have your traditional normalization when it comes to quantum mechanics, and then there's one big thing you got to know about like quantum computing is that when you measure a state, its probability collapses, right? You've gone into one outcome, so you know it's 100% probability in that outcome at that point in time. So you collapse what they call the quantum state, and this is considered a master equation for all the possible quantum states that you can have. It's a bit hard to go by, but the cosine and the sine here, they just, your basic trigonometry, cosine squared plus sine squared means keeps it normalized. So if you know it's your theta is 0, then you have a whole complete chance of being in the 0 state. And if your theta is 180 degrees, you're in the 1 state. We'll explain why theta is divided by 2 in this circumstance, and it's actually with the Bloch sphere in the next page. But before that, I was just say that here's your phasing term that we talked about. Yeah.
Sorry, what is the difference between so you can have a probability amplitude that's 1/√2, you can have negative 1/√2, you could have 1/√2i. What's like the physical like significance of like a negative versus an imaginary part? Like, what do you mean? What's the out of phase part like?
So phasing, how I interpret it is just that there are certain actions that you do that it's like several things can do the same action, but one action will just cause a color to the probability amplitude, and so. That's a question. Sorry, could you elaborate a bit on what you're trying to ask?
Yeah, because I was like imagine like when you add probability amplitudes, right?
Mhm.
Like one probability amplitude is like the negative of the other. They like
Yeah, they cancel out,
They
and then
cancel out.
that's the like interpretation of negative probability. So if you know, like if we have 3 plus 4i, this is not going to be normalized, and we add 3 minus 4i, you all of a sudden you have 6, which is an amplitude much smaller than the 3 plus 4i or the 3 minus 4.
so that's like the interference part.
Yes.
And then
And-
so that and the phase part of it would be that I know this isn't like exactly correct, but the complex numbers that are needed to describe the different phases.
Yes. Yeah. And it's rectangular form is what this is. It's easier to see like how the interference is happening, because if you do I plus minus I, then it goes to 0, and there's 0 probability amplitude for that state. And then the phasor notation that we use, which is the R times e to the I phi, it's more useful for when you're doing actual like operations on quantum states. And so
there's a sign of the qubits. This form is too attractive. You can just think of cat 0 is a column vector of 1, 0. Cat 1 is a column vector of 0, 1. So this corresponds to the vector basis I talked about before in qubit spaces.
Mhm.
If you just want to forget anything about the physics and just want to do calculation, you can just interpret it in this way.
And then just as a follow-up, so does interference occur when the phases are different then?
yes, that's so if two things are in phase, it will be constructive interference, and if two things are completely out of phase, that's destructive interference. And so in a it's like R e to the I phi.
For wave example, it's like
Yeah.
Q cosine out of this.
Yeah, I can do that, but I just wanted to put this down real quick. Plus R e to the negative I phi will be 0. So
I think what you're getting to is how do the numbers relate to something that's actually physical, right? That's what I thought we're getting to. And Reese has brought up this concept of interference, and it is not a required background or anything, but interference is a quantum physics thing to know. So it's just for understanding, but if people do not understand what is going on here, just what Yital mentioned about thinking about ket 0 and ket 1 as just column vectors, that's all you need to do calculations and understand how it works. But that's a great point that you brought up. People usually take it for granted as to why we even need an angle, or like why are we representing probability in complex numbers. And I would recommend people who are asking questions to introduce like
Oh yeah, my name's Natara. I'm in the 3rd year CS major.
yeah. So actually, my previous explanation wrong. It's not e to I negative phi that gives it. It's R e to the phi, and then pi, which is your 180-degree rotation, is out of phase. That will give you 0. And it's apologies for my bad writing, but actually going back to this complex phasing, the standard notation, we always put our complex phase on the one outcome when we're talking about a qubit, because otherwise we would be referring to a combined phase between the two ones. And now we call that a global phase, which is irrelevant to the computation because it will do a correlated effect. And so this will be your and this is your probability relation. And I'm just going to jump in from this psi here to describe the Bloch sphere, which is it's a pretty hard concept to first visualize, because if you look here, we have essentially two angles. You have theta and you have phi, which if you extract it away, that can give you a coordinate on a 2D sphere or a 3D sphere, where your theta is your angle from 0, which is your probability transfer between 0 and 1, and phi is your complex phasing, which goes along the xy plane. And we like to say that our main axis that we read out from is the z-axis. So you'll sometimes see like measuring 1, but you also may see people say measuring in a z basis. And then any point on this sphere is a normalized vector, like coming from a unit circle. You just generalize it to the spherical coordinates, and then you represent a pure state. So a pure qubit state is going into like next lecture is entanglement. And so if you have two qubits, they can have non-classical probabilities, or they can have correlated probabilities. And so instead of being in just like both having two heads or tails, like, okay, if you flip two coins, and classically you would say that you have equal probability of either any outcome, heads to heads, heads tails, tails heads, or tails tails. But correlated probability, which would degrade from a pure state, can have either heads heads or tails tails, but no other probability. And
don't worry about entanglement.
Yeah.
Right now we have like a few slides at the end to address it in a more mathematical way and a simpler way.
Mm-hmm. And then, yeah, here are some common states that describe like superpositional states. Something that superposition generally does not. Yeah.
Say question. I don't know if I missed this earlier, but how are Ket0 and Ket1 defined?
Oh, so Ket0, you should think that it's a mathematical way, it's a quantum vector of 1, 0, and Ket1 is 0, 1. It's like a two.
Okay.
Yeah, that's why I access in 2D space.
Yeah. So if heads and tails will be 2D, and we'll get further down, like a 6-sided die would have 6 dimensions, because each is a measurable outcome. And there's something to note is that these superpositional states where alpha or beta can be some value between 0 and 1. So that means there's probability both sides, just like in the Schrodinger cat example. Up here, there is that doesn't really describe the phasing. So you have this positive phase here, or this negative state, and these actually occupy different axes. So if you see the complex value I, you're probably on the y-axis, and if you see like 0 plus 1, so there's just a positive or negative sign on your superpositional state, then you're on this x-axis. And the x, y, and z axis are very important when it comes to like doing quantum operations, because they provide the different axes which you can do operations on. And then if you see this little master equation is back again, maps to x, y, z. It's a little convoluted, but sine theta, cosine theta is your x. The big one is like cosine theta, which is just your probability. That's your z-axis. Z-axis of 1, if you're the 0, 0, 1, then you're on a probability of 0. But if you're in 0, 0, negative 1, then you're in a probability of 1, or just being in state 1.
I
And
always refer to this projection into normal x, y, and z axis. if you are not sure about how to visualize it, I think in your like, favorable way, you can just calculate the direct coordinate, and you can confirm that cat plus is in x-axis and so on.
And you,
So just to clarify, you can have both negative probability amplitudes and negative.
so negative probability is a kind of a buzzword. There's no real representation of negative probability. You have negative probability amplitudes.
Okay.
And the fact that it interferes with each other, coming to like this part, that probability of some outcome disappears.
Okay, but for the literal like probability of the like two of it being in the two states, that has to sum up to 1, and
Yeah.
those are positive.
Yeah, for all three of these states, there's a 50% chance of being in 0, and there's a 50% chance of them being in 1. And so that really describes the fact that you can't see phasing out the readout. Phasing is just some complex value that's just like the color of the axis, which doesn't make sense when you're reading it out.
So the fundamentals of probability summing up to 1 is still true. So amplitude squared, the sum of amplitude squared, sum up to 1. And amplitude squared is the probability.
Yeah, right. And that's like the difference between probability and probability.
Another question.
Yes.
I understand the planar side of things. So how do we just move along the sphere if the surface is sphere? Or
Yes, if you remember like your unit circle from trigonometry, it's just it's that, but with 2 different angles, which is your theta and your phi, which coming from this quantum, like your master equation for representing a quantum state, your phi is your phasing, and then your theta is your pretty much angle of superposition.
Maybe I missed this, but does phase like represent anything, or we're just talking about like the concept of like
So there's no like real representation of phase is the best way of saying it. So
which is math?
yeah, that's one of my major concerns with it, is it's a lot of math, and it's the only like real readout you can have from this is if it's 0 or 1. But quantum mechanics says that in its evolution, or when you're working on it, you will accumulate relative phases, and that. So I like I said earlier, it's like math says that you can have complex phases for any of these operations, and it's quantum mechanics that says these must exist to describe certain phenomena, especially certain actions must accumulate a phase. Yeah. I like to think of it as like it's not a real quantity. So I keep on saying it's you have some distribution of probabilities between 0 and 1, and the phase is just some color for that, and it has no real meaning outside of you do something and somehow a color, like your vector is now green. And I'll just go back and represent qubits using our vector basis again, where 1, 0, and 0, 1. Alpha, beta, just coming from up here, would be your different probability amplitudes of the vector. And then, yep, here's your superpositional states, and here's your standard superposition that, like Schrodinger, this is like your Schrodinger's cat state, and this is Schrodinger's cat state, but somehow it is incurred a phase. And then now let's describe the probability again. In quantum mechanics, probabilities are calculated for amplitude. It's very specifically that this magnitude squared, or the length of the vector squared, is what gives you your probabilities. And then total probability sums up to 1. That's why we keep it as a unit vector. And then when we measure a quantum state, just enforcing this, is that we're projecting it onto one of these states. So it's either your 0-1 basis, or your 1-0, or your 0-1 basis, where alpha squared probability for that, beta squared your probability for that. And then here's just like going into larger dimensions with quantum states. So let's say we had a D8, and then you would have 8 different outcomes, you would have a unit vector of size 8 when it comes to the spaces. And they will all, the probability amplitudes will all sum up to 1. But if you look 1 over square root 8, you'll get to 8 over square root 8, which is not 1. In fact, it's more than 1. And yeah, multiple qubits expand the state space exponentially. So if you go back to your tensor product, if you have 1 qubit with like a 1-0 state, you would tensor it with another qubit in some other arbitrary state, and then you will get a bigger state that is alpha, beta, and 0-0, because obviously this 0 state here doesn't have any probability of existing. And notably, if you do this, you actually preserve the probability. Multiplying them together means that they all stay in the same, all the probability amplitudes all sum up to 1 squared. And then here it is again, just with the Brockett notation. And you can see that 0-0 goes to 1-0, 1-0. And there's always, if you have 1 state active and it's not in superposition, you're always going to have 1 state active. And that's how it preserves the probabilities, or the unit vector nature. And then just a bit of a side note, this goes back to even like binary representation. Everything you represent must be in base 2 to work with this tensor notation. But so like something that's like a die, a 6-sided die, could not be represented in base 2, right? The closest one would be 8 states. And this is like 2 to the 3 actually would be the dimension. And so there are ways you can actually represent it using 8 states. We just, to delete the probability of being in the 6 and 7 if we're in binary, if we're going from like 1 or 0, 1, 2, 3, 4, 5. So 6 minus 1, I mean, from state 0 to 5 will be have probability.
Yeah, this stuff is usually called encoding.
Mm-hmm. Yeah, that is state. It's called state preparation and encoding, and that is one of the big focuses of working with the quantum computer, is preparing your state to calculate on. And then entanglement a little bit more here. If you see that we have this linear combination, instead of tensoring, we have pretty much 0 tensored with 0 plus 1 tensored with 1. And that's because we cannot actually represent this as a tensor decomposition of 2 different vectors. So like if we did a 1 over square root 2, 1, 1, tensored with 1 over square root 2, 1, 1, we could not get this entangled state, because it would sum up, go out to essentially 0.5, 0.5, 0.5, 0.5, which is the closest decomposed state to that.
In a mathematical way, if you want to use tensor product between 2 qubits, you have 0, 1, 1, 0, 0, 0, 1, 1. So maximally you have 4 combinations. But for a length 4 color vector, you have 2 to the power of 4 potential outcomes. So that's why usually there's a lot of space imposed by this kind of entanglement operations.
Mm-hmm. Yeah, that's actually a bit of the power of a quantum computer, is that for every bit you add, you have pretty much to the n states that you can store information in. Whereas for every bit you add, you have 2 states you can store information in classically. And then this is more concluding the Marxist-Moroi bridge, but I just want to cover everything once again, just make sure that it goes in a more concise way. The quantum states, like in your Brockett notation, are always as a unit vector and as an array of complex valued outcomes whose length corresponds to the number, or whose dimensional size corresponds to the number of possible outcomes. So for coin flip, it's 2 outcomes. For a dice, it's 6 outcomes. And the unit vector makes sure that it always normalizes to 1. And then for binary bases, which quantum computers use, the dimension is always of size 2 to the n, where n is the number of qubits you have. And then for human readability, we use Brocket notation, which is just your and that is, and mostly this is computers use, the entire matrix state, but Brocket lets you, especially within like these highly correlated or entangled states, you can write them simply instead of writing out every single entry in the column vector. And so it makes it very human readable. And then there's, like it says, it's a clear representation of almost every quantum state you can have. It's a convenient structure for quantum calculations because you can operate on each of these Brocket states independently. These are essentially their own little probability vector that you, even though they're not normalized, if you sum out all operations, they renormalize again. And then the reason we use Brocket is very easy to represent the complex phase, even high dimensional. If we have highly correlated states, we can represent literally 0, 0, 0, 0, 0, 0 plus 1, 1, 1, 1, 1, 1, 1 highly entangled state with just 2 ket vectors. And that is very convenient when you're working with these very high dimensional states. And then this is foundational into like reading in any literature with quantum mechanics or quantum computing, because they'll use this as shorthand for states. And then, so what we've introduced right here is in this lecture is, a quantum state, all the possibility, the unit vector of all the possibility outcomes, which is essentially a data encoding that you'll be putting into your quantum machine or your quantum computer. And so it's like, how is this data useful, and how can we even operate on it? So this is the reason why we use these normalized state vectors and not just direct probabilities, because we always know that state vectors must have length 1. They're unit vectors. So we know there's a class of operations preserve unit length, and in very, very helpfully, these all can be written in matrix form. Unit length preserving operations are in matrix, can be used represented in matrix forms, and they have a special name called unitary operations. Unit vector, and as the Bloch sphere might have suggested, there are 3 basic bitwise compared to like the classical 1 bitwise function that you have for each one. So if you see on this Bloch sphere up here, we have 3 axes. You have your x, y, and z axis, and that comes down to actually, I gotta ask a question for you. Do you know what type of translation, rotation, or scaling or shear, which one preserves the length of a vector? You remember your geometry, what preserves size? Yes, but if you're looking at a vector, the head of the vector where you're pointing to moves away from the origin, which is your tail. So your length of the vector changes with the translation. Yes, that's rotation. And pretty much every quantum operation could be viewed as a rotation and an arbitrary axis in that's the unit vector space. And for like the Bloch sphere and stuff, you always see like X rotation, Y rotation, Z rotation. Yeah.
So I take it that you don't need to like in applications you don't need to learn the program system. It's just always like the algorithms change.
Yes, it is. In like larger like multi-qubit systems, the Bloch sphere is you're having like a 4-dimensional Bloch sphere. Like it's you can't visualize it. But if you're looking at like a 1-qubit operation, yes, everything that is a 1Q operation, you can see as a rotation on the Bloch sphere. And so, and I was going to do a sneak peek of quantum operations, which is what is next week's material. If there's something called the Pauli matrices, which was Pauli was the guy who discovered that in complex numbered space, you have 3 axes of rotation, and then actually Bloch was the one who won a Nobel Prize for that. So, but linear algebra is what makes this so convenient to work in a state vector form. Again, you can use what's called density matrices, which is just a pure probability form, but you have a lot more numbers to work with. So in computer science, we always talk about like a universal gate set when it comes to like something that is Turing complete. Can you calculate it using these number of gates? Our universal gate set is what's the X, which these polygates, which are X, Y, and Z rotations, and some multi-qubit gates, the C naught, and then R theta is actually a single qubit, but is an arbitrary rotation against using these X, Y, and Z axes. And the easiest way to think about this is this changes from like truth table notation where one state goes to another one to matrices, because if you're in a superposition of multiple states, you can't just have a truth table to write a transfer from one state to another. You have, and this is also where you get these complex phases accumulating, is that these operations multiply by complex number. And then, yeah, we'll talk next week about representing circuits and multi-qubit operations, but we're starting to get short on time, so I just want to get started with the actual workshop section. And I want to represent these poly operations operating on this Bloch sphere. You have your X, Y, and Z. So your X is your standard like bit flip, where you go from 0 to 1 and then 1 to 0. And then let's see, Y is your same thing, but it includes a phasing to it. And actually Y is more like a combination of X and Z. So Z is a pure phasing. It's an action that preserves the probability between it, but it will change the phase of the one state. And then just a thing very often used in quantum computing is the Hadamard gate. And we usually call it like the fundamental superposition gate. It's just the one that will make, if you operate the ket 0 state, will put you in that Schrodinger cat state, that superposition state.
Could you give us an example of these matrices actually acting on the 0 state and the 1 state, so we understand how that's like, for instance, the X gate, can you show us how it actually could be flipped?
Yeah, so here's we'll start with the 0 ket. Will being in the vector column vector form is 1, 0, and so operating on the x on this 0 state, which we always in matrix multiplication we go from right to left, and so 0 gets multiplied by the x. If you put it into the X matrix, we get, and that will result into the vector 0, 1. Sorry, but if you take this, multiply it by the dot product with the 0, 1 vector, 1, 0 times 0, 1, they're orthogonal, so you're going to get 0, and 1, 0 times 1, 0, you'll get 1.
So it's basically like a classical NOT gate, which transform 1 to 0 and 0 to 1.
Mm-hmm.
It also shows the Z gate, so confused about what the is.
Okay, so yeah, a Z gate, let's work in the simple superposition state, which is just 2 plus equals 1 over square root 2, 1, 1. And then operating on the Z gate, we get, I'm gonna actually move the 1 over square root 2 over here, and that's 1, 1. We get 1 over square root 2. If we 1 times 1, 1, 1, 1, 1 times 1 equals 1, and then 1 times -1 equals 1, -1. And then I actually want to get into the workshop here because it's actually simpler demonstration of how the gates work.
So when it's so true.
Yeah, I'm gonna move this over here.
Okay. Oh, that's fine.
Here's IBM Quantum Composer, the toolkit for this. And so if you all have this up, I'm just gonna tell you to change this number right here, Q to 1, because we're only working with 1 qubit right now. And then I'll just give you a little tour of it. So this area right here is considered your circuit area. You can drag and drop gates from over here. And they label this out more for what like a computer scientist or like somebody working with quantum computers would actually look at it. But you have your standard poly, your Y not is sometimes is represented as this, or X is represented as this because it's just a NOT gate. Here's your controlled NOT, and then your Z is right here. So I'd like you to, here's some other stuff. So here's your probabilities, and if you could just drop down, you can choose state vector too. So I measure, where's my measure? Right here. Yeah, so if you're measuring out right now, you'll see that your probability is 1 and your state vector is 1.
Just a little bit on the notation. The C here represents classical bits. The Q is the qubit we are using. So when measuring, we are actually storing information on classical bits, as shown here.
And then if we add the classical superposition gate, the Hadamard right here, the H, you'll see that the probabilities go to 0.5, 0.5. Oh, this is not updated. Oh, it's because I have to measure a gate here. Yeah, that's it. It really tries to enforce destructive measures. So if you're measuring over here, you'll see that one of these will collapse to one of these states here. So I would, and it's, yes?
But why would measurement with the physical probability on the left side, why would they just have a small difference after? Take it away. On the left corner, the 2 blue bars, if I put the measurement in after the H, then it would have a slight difference, 47% for state 1.
Okay, so yeah, so something that happens with quantum computers is we run it by shots. So that what happens is when you measure, you collapse into one of the possible states.
It's like for 1 coin.
Yeah.
For one.
So it's like the state vector will say, okay, you're going to result in this state, or you're going to result in this state. And so if you think of heads and tails, it's 50% probability of being heads or tails. But if you do like 100 runs, you're never going to come out with a probability of exactly 50% between the two. There's always
what the measurement does, is like, in some of the trials.
Yeah, some trials will be heads, some trials will be tails, and
and also later on, you will see that the quantum computer is noisy. So what you design the circuit is not like the output is not exactly what you want. You have to plus noise.
There's always like a noise level. Sometimes people view it as like every probability is just a small non-zero chance that your algorithm dictates there shouldn't be, but just because of noise, it will be there. And then I would just like to show off some entanglement real quick. So, or not entanglement, but interference. So in the superposition state, if we apply a phase to our right qubit, right, or our 1 state, you see that it's now phase angle of pi. We've put a complex phase on it. So then one of the big things about Hadamard or entanglement gate is that if you apply it twice over, you get back your original state. It's invertible, right? It's its own inverter. But if now, before we return it, we apply a phase to our 1 state, and then does any get a guess what's going to happen once we put back another Hadamard on it? Yeah, actually, yes, because Hadamard is essentially rotating it onto the X state. And then if you do a Hadamard again, a 90-degree rotation rotates you after you phase it, flip it 180 on the Bloch sphere, turn it around on the 190, it will be into the 1 state, as you see here.
So that's the X state. But don't worry, if you don't get this intuition, you can just play the matrix multiplication and see what it does. That's how I do it always. Because I don't have this kind of intuition. I'm an electrical engineering student. I don't study quantum physics for my life. So I just learned to do matrix multiplication and still doing well.
Unfortunately, that is the downfall of me, as I've been studying quantum computing for 4 years now. So it's not. So here's a little something else. So S and T, these gates right here, these are considered the like a partial rotation of the Z gate. They're your R theta gates. So this is actually would be considered, if in matrices, there's an operation called the square root. It's kind of similar to like square rooting a number. If you multiply a square root by itself, you'll get the like square root A times square root A will give you the matrix A. And it's the square root operation, again, gives you some really weird complex values. But now if we do the square root of Z, do you know what will happen? It doesn't do a full 180 rotation. So okay, let's see. Let me show you on the Bloch sphere. Actually, we have that right here, quantum sphere. If we or actually this is a state sphere, so it's a little bit different from a Bloch sphere. But if we start at H, we have our superposition of 0 and 1. They like putting multiple states as their own vectors. But if we put the
we need to check the space angle on the.
I was just going to put the number. This is the Q sphere, so it's used for higher dimensional state representation. So the Q sphere people use when you have like 8, 9 qubits. You see what states are active, and not like the Bloch sphere, because your phase plane is like right here and your bit plane is right here, your bit axis. So if you put, I'll just go back to this. If you put your S here, you accumulate a phase on your one state. Go back to the state vector, and S is actually a 90-degree rotation, where a Z or an X is a 180. And so if you put an H again, you get the exact same state. Because if you does anybody know why? Okay. Well, the thing is, so what happens is you rotate onto to the x-axis with your Hadamard gate, and then the S gate, what it actually does is it rotates around your z-axis 90 degrees. So all of a sudden you're in the y-axis. And if you try to do a Hadamard, which is a rotation of the x, a y rotation essentially, you stay on the y-axis. Nothing happens.
So what I saw is that if you just throw in the SD, it's going to give you phase angle to pi over 2 for state 1.
Yes.
And then when you throw in the H, then it seems to me that it rotates by, and then the 0 state becomes pi over 4.
Mm-hmm.
And then state 1 becomes pi over 7. How is that, like you mentioned, spinning 180. That seems like then spinning 180 spin pi over 4, but misunderstands the question.
So that's your phase angle. Yes, that's your phase angle is your z-axis rotation. And best way to explain it is that if you do a Hadamard gate, which I don't have it up here right now, it spreads the phase between the 0 and 1 state. And so
is it like putting it into a superposition, so you don't know where it is between?
Okay, so we do know where it is. It's so
I just multiply the matrices and trust the process.
Yeah, I'm sorry. I just don't have I have a Bloch sphere visualizer. I can just use that. Let's see. I want to give you guys a little bit of homework with these 1 qubit rotations, just so you guys understand it a bit. Don't worry, will not be entirely well. So here's your x-axis, your y-axis, your z-axis. Your bit flip is just you add one of that. And so if I just remove the quantum gates, actually, you know what? keep the quantum gates because these are your poly Z and stuff. Can't actually see this. Okay, yeah. So if we start off with our Hadamard gate right here, right? That puts us on our x-axis. And so if we do Hadamard again, we just invert it. This just should be a hint because I want to see if you guys can figure out how to make a Hadamard gate from the poly gates. But and then now if we do the Hadamard and then the Z rotation, we'll flip it and we do the Hadamard again. We get to the one state, and that is your interference. Your interference looks much weirder on your Bloch sphere, but if in the matrices, it's much more clear when you have the negative state vector. And then I'll just.
Could you hit the Z again and then H? So the way how you had it before.
He's talking about first T and H.
And like you want it this way?
Oh, yeah. So how did you do this? Starting from the top, like
So you start with an H, Hadamard, right? And that'll put you in your superposition state that we traditionally say is the X plus state, because that your negative is your X minus over here. And so that is your 1 over square root to ket 1 plus ket 2, or ket 0 plus ket 1. So, and then Z will translate to that to 1 over square root to 1 minus, or 0 minus 1.
And then that's how we started out this way from X.
Rotated 180. And then when you rotate 180, that your phase turns 180. If you again do the same Hadamard gate, you interfere and all of a sudden you go to 1 instead of 0.
I see. And is it like geometrically speaking, you spin it down to that way, so you kind of apply the same operation?
Yeah. So that's part of Hadamard, is that it's invertible. It's a little secret here, but Hadamard is an arbitrary rotation that happens right between like the 0 and X axis. It's just like this diagonal right here, it's the axis of rotation. And now that'll give you a little hint of how to figure out how to do Hadamard from poly gates. And then if we and then we do H, and then our S gate, which does only a 90-degree rotation. If we do the Hadamard again, we're all of a sudden back on the axis. And if we just doing the Hadamard again, we're on the other side. And we get this, we're locked in this x-axis now.
And we keep getting Hadamard, and we just go back and forth.
Mm-hmm. Yeah, in a more classical sense, if I guess aerospace guys will say like this is gimbal locking. You're locked on an axis with your rotation. And then the T gate's even like a smaller. This is a square root of the square root of the S, so it's a 45-degree rotation. And you see that these S daggers and T daggers. This is your this is more next week, but these are called your conjugate transpose. It's the same thing as like having the bra to a ket. There must be its own. It must be an inverse to that gate. So S dagger is the inverse of S. So if I put T right here, if I put T dagger, you go right back. And then I just wanted to show this workspace. And I'm going to jump back to here. Just put it as clear. Well, actually, you know, I'll show you. Mm-hmm.
This might be like a very stupid simplification, but just on a high level, like the difference between a qubit and like a bit is that, so bit you've got 0 or 1, and now with the qubit, the representation is that Bloch sphere that you showed. Like
yeah,
that way, like we just have a whole new range of values.
Mm-hmm. So that, like, I'll post the notes, but what we have is a classical state. You're either in 0 and 1, right?
Right.
So your vector is either 1, 0 or 0, 1. That's always going to be, and you have what's called a probability transfer matrix. It's pretty much your truth table. It says if you're in the 1, 0 state, you change to the 0, 1 state kind of thing. But
yeah, there's another way. So I guess you know the one-hot encoding, right?
Right.
Right. So if you encode like 0, 0, 0, 1, 1, 0, it's like in binary representation. You have 4 possibilities, right? That's also true for qubits without entanglement, because if you use the tensor product between 0, 1 and 1, 0, it's basically doing the one-hot encoding. But means in entanglement, you can actually have more than one appearing in that column vector. So if we have like a 2 classical bits, we have 4 possibilities.
Right.
And representing 4 one-hot encodings. But these 4 one-hot encodings is another base for what qubits can represent. So because it's like a length 4 column vector, we have like in total 16 possible combinations.
Here, I'll actually put the
So in terms of space, that's one difference between classical bits and qubits. So the possibilities can represent much larger than classical bits.
yeah. So in our quantum bits, we have the 0 and the 1 state as like a bit.
Right.
And so that now we have these new parameters alpha and beta that correspond to the probabilities of, or the square root of the probabilities of being each one. Classically, either alpha or beta will be 0 or 1. There's no intermediate probability. And so it's qubits can, unlike classical bits, qubits can exist in a continuum of states between 0 and 1. And then show real quick like a 2 entangling state. It's 2. Here I'll show what the C naught action does, which is if the control qubit is 1, it will bit flip the target qubit. So this is the control qubit, this is the target qubit. And here we have a non-classical state, or we consider a highly entangled state, where if we put a Hadamard, so it's in a superposition of 0 and 1, all of a sudden we now have only the 0, 0 or the 1, 1 state being possible.
That's the best.
The Bell state, yeah.
Yeah, that's probably the easiest way to create entanglement between quantum gates. It's just 2 gates, 1 A and 1 C naught.
And yeah, it's now once if you have 2 qubit gates, which is the C naught gate, and 1 qubit gates, you can generate any arbitrary gate on any n qubits. So sometimes it will take a lot of gates, and that's actually a fundamental limitation of this simple gate set, is that there's the universal gate set, or the Soleil-Chiata theorem, is that there's this T gate here is very important to make sure that you can make any arbitrary rotation. You'll see like in a compiled quantum circuit, you'll have hundreds of these T gates in the circuit just to make a small incremental change, because if unlike like the S gate, which it's square, and the Z gate, the T gate has a smaller effect, and it does distributes the probability unevenly. I'll actually drop this back to 1 qubit. I'll actually finish up. So on this right side, which I've been working with right here, this is called Quasum. If this is essentially your quantum computers assembly language. Though actually, if you've ever done anything with like they call it FPGAs, or like any like integrated circuits, that this is called HDL, hardware design language. So this will just say like, here's your registers, here's your gates between the registers, and then your measurement at the end.
Yeah, to start, you can first draw the circuit and then just extract the code.
Yeah, you can drag and drop anything you want from this section here, and you'll update it,
and the code will change.
Yeah, you can actually work with their higher level, like the Python invitation. It'll show you the entire Python code you need to do it. And that will actually be the subject from week 4 on, is we'll be using the Python code, because we'll be working with algorithms on quantum circuits.
This might be a super question, but
Oh no, nothing's.
but like, why is this like so powerful? Like, what can you now do that you couldn't have done before?
So there's 2 major advantages. Like as this quantum state says, when we have 3 bits, we have 2 to the n states represented. Where a classical computer, for each bit added, it only has 1 more state represented, or you have 0, 1. And so another thing is that with quantum computers, you have things like interference. So when you do out these calculations, all of a sudden a different probability shows up. You can do this classically too, but like I said, it's computational difficult to do these
So it makes
quantum
some
data.
computations more efficient, essentially?
Yes, and then data encoding with like quantum computers is just exponentially better.
Right, that I can do.
And also as a metaphor, if you have watched the Avengers, you can just use like the Doctor Strange because he actually observed all possible combinations of actions and find the best results based on his observations. That's the same as our quantum computing because we are in superposition of states. So basically, we have access to all possible outcomes, and these outcomes you transfer to classical computing, you have to try one by one.
Okay.
So if you take computational theory class like CS181, especially with Professor Mehta, he covers this at the end as an optional topic where he says that from a theoretical standpoint, a problem that can be solved by a quantum computer can also be solved by a classical computer on paper, but not in reality. So the efficiency of like the power is only giving us the ability to actually solve it, like not like on paper. So you cannot. We know that like encryption can be broken using a quantum computer, but we need a quantum computer to break it. Like there's a difference between theory and practicality, right? That's basically the difference. If you think about where quantum computer is helpful or shines, it's basically enabling us to solve the problem that we're solving. Like there are different categories, like you know how NP hard and
Right.
there, like quantum computers have their own classification, but you can think of it like enable to solve code unquote NP hard problems, which are not in a time sense, not like a mathematical sense, because in theory it is complicated.
Yeah, and we will show sample algorithms that really demonstrate the potential quantum advantage they have. And you will find that we usually, at least we have a quadratic speed up.
Quadratic is you would think it would be exponential for most like quantum algorithms because you're doing exponentially growing states, but quadratic seems to be a very common factor when it comes to these speed ups. And I would say I don't want to give you actual homework, but I would like to ask that you guys, if you want to take a photo, or I'll post these slides too. That if you want to get more understanding like Hadamard gate or just the poly gates themselves, we'll go over them next week. But like try figuring out how to do a bit flip with only the Y and Z gates.
Yeah, you can just experiment with the quantum composers, like going like random gates and see whether it's actually the same gate and other gates. And the last picture is more like my part. So you're just trying to prove some properties.
Yeah. So this is a bit complex because we haven't really dived into Hilbert spaces, but Hilbert spaces are literally, you get your qubits and then you tensor them together. It's coming from here. This kind of a statement is like a Hilbert space. So it's an n Hilbert space has n qubits. It's just a formalism for tensoring together.
Thank you.
Yeah,
Oh, sure.
sure. I mean,
Let's say that in classical computing, we have